then try the other approach. I would never say no to that. Please, dear God. I am in the office for a reason.
But how much questions? So yeah,
Say again?
if we come to see you.
Yes, I can help you with whatever I can. I can totally help with statistics. Totally. But I help, sometimes I get people that, old students that aren't even my students anymore, they come by. And they're like, I'm in this class now, do you understand this? Yes. I love it. I tell them my priority is my current students, but still. Okay. So last time we worked on a handout, right? Maybe not get that. You should have all gotten it, because one side was the answer key for the practice quiz, but it's possible you didn't. Anybody else need that? It's one side is the answer key for that practice probability quiz, and the other one is the thing we did last time on section 4.3. Binomial, yes. The one about smoking San Diegans.
Practice for the double quiz?
Yes, so on the other side it says section 4.3, binomial probability.
Did we do it?
Yeah, well, a lot of stuff. Yeah, we did it last time, remember? Yes. Yes. Sure. So that was from section 4.3. So not surprisingly, we're about to get into chapter 5, guys.
I thought we were in chapter 1.
Let's see. It's okay to visit, but you better not distract me or them. All right, guys. So let me see if you guys can tell me that. Give me an idea of chapter 4. We did the binomial probability, right? So an example of a binomial probability would be left-handed people. What's probably get exactly 11 left-handed people if I pick 80 people, right? That kind of thing. What chapter 1 terminology would describe that kind of situation? What kind of data would that be? I can get 0 people, 1 people, 2 people. What kind of data is that? What kind of discrete? I love it. So chapter 4 was all about discrete probability distributions. Remember, the very first couple sections was about x and p of x stuff, right? If it was continuous, ain't no way I can list all the possible values, because continuous takes on an infinite number. I don't want to make a table, then oh shit. So chapter 5 is all about continuous distributions. What to do then? And we're headed towards chapter 6, which is really almost the most important chapter in this book, in this semester. Chapter 6, just to kind of get you ready for that. All right, you guys look appropriately excited, which for some of you is not. Oh well. I do, of course, you know me, have a little handout we're going to talk about here in a bit. But let me do this. How many guys throw darts at all? Anybody throw darts? You have to be a certain level of inebriated to do that, or sometimes that's a requirement. Everybody's seen a dartboard before. Okay. All right. And there's a lot of different kind of ways to play darts, to throw darts, to play darts. I'm not going to draw the whole damn thing. It goes around, right? Some of you guys are like, geez, no. That little red thing in the middle, it would be red. Well, what's that? Bullseye. I like it. And the most standard classic thought of game, that bullseye is, points-wise, is how related to anywhere else. The highest, right? So not every game related, but a lot of them are. And you got these little bands on here. So if I get into one of these big green sections, normally that's going to be a lower score, right? Kind of depends on the game you're playing. And if you get a bullseye, normally that's the highest score, right? Why do you think that is? It's kind of related to, is it very likely to win the biggest prize in a jackpot, in a lottery, to win the biggest prize? Is that really likely? No. They're going to make that very unlikely so you don't have to pay out a lot of money. So why is this very unlikely to get here? Even if you're really skilled, it's still kind of hard to get there. It's really small. I like it. So the points I give for one of these big areas here should be less compared to the ones there because it's so unlikely to get in there. In fact, why is it unlikely to get in there? If you're a bad player, and I only count the darts that actually hit the board, so I'm not going to count those. You see what I mean? I remember my little brothers and I, we had one in the garage, and man, the wall around that was just devastating. So I only count the ones. I only count that one, and I count that one, and you're like, oh my God. If I only count those, and you're just kind of randomly throwing it at the board, it should not end them there very often. Now, how can I make it more likely to hit the bullseye? What would I actually have to do if I made my own dartboard? I want the bullseye to be like really easy to get. I just have to make it bigger. All right, I love it. There's a very basic idea that unbelievably leads through 5 and 6. And a lot of students don't believe it because they're like, it can't be that easy. But the probability of getting a dart in one of these things is related to the area of that place, right? So probability is related to area, if you have it, a visual of it. All right, how are we doing so far? So probability is related to area when I have a visual. And there's a few other requirements, but this is the basic idea I want to get across. Okay. I like it. So, one place we've already seen this in action is when you make a histogram. If I have a histogram and I got something like this. Let's say this is 5, 10, 15, 20, 25, 30, 35. So those are ages of people. Blah, blah, blah. I got labels so nobody can yell at me about blah, blah. I get to yell at you. You can't have them. What's the most likely range of ages for somebody in this sample? Oh, God, Jeff. You're all like, finished writing what you're writing. Yeah, well, obviously, if you can't read it, which bar would it be? The tallest one, right? Now, supposedly, please to God, I understand I can't draw worship, but what's true about each of these classes? They should all have the same width. So why is this the most likely? Another way of answering it, not just because it's the tallest, but because it has the most area. I love it. Kick ass. So when I'm given a visual of the probabilities, the probability of a little piece of it is related to the area of that piece. Okay. I like it. So far, how are we doing? This is sort of hard to believe, but it's actually exactly the idea. As long as the total area of the picture equals 1, then the area of a piece of it is exactly equal to the probability of that piece. Why does that make sense? What do all the probabilities in something have to add up to be? 1, or 100%, or 1 as a decimal. So if my visualization of my probability stuff has an total area of 1, the areas of the subpieces are exactly the probabilities of those things. And right now, you're not really sure what to make of this. So let's do a concrete example. The very first kind of example we're going to do is called a uniform probability distribution. When I say the word uniform, what's the first thing that comes to mind? The same. Or does somebody have a type of person in their head? Soldier. Wearing a uniform. And of course, every soldier is wearing the same uniform, basically. You can look at the little details and shit, but they all basically have the same freaking one. Especially if they're all the same rank, just marching along, you're like, it's the same person over and over. Sorry. Technical place. So we've got something called uniform probability distribution. So the word uniform relates to how the probabilities are distributed. So most of the problems we did in the x, p of x section were not uniform because the p of x's were all different. Maybe a couple of them were the same, but they were basically different. So if I had something like this, well, that would be discrete. Let's do a continuous one. If I had something like this. This would be a uniform. Now what's the example is? I remember very often going to a different city and there's some kind of shuttle at an airport that takes you to the next terminal because it's about 7 miles away. So if you miss that shuttle, you're like, oh God, I got shit. And so that's, I'm speaking from experience. Just barely miss the shuttle. So the shuttle comes every 20 minutes, let's say. Oh my God. If you just barely miss it, how long are you going to have to wait for the next one? 20 minutes. If you get there right when the shuttle gets there, how long do you have to wait to get on the shuttle? 0 minutes. So it's uniformly distributed between 0 and 20. If you randomly show up, then any time between 0 and 20, you could wait any of those times with equal likelihood. Is that understood? No times would be more or less likely, except in your own mind about Murphy's Law. I always wait the most. No, we just forget the short times we wait, and we remember the long ones. All right. Okay, maybe. Do you understand now a little bit better? Uniform probability. There's nothing that's more likely than anything else. I like it. Notice how the continuity is displayed here. And what does this axis represent again? Fundamentally? What we were just talking about? Time. And time is definitely what kind of variable? Just time, not as it looks on a watch or anything, just time. Continuous. I like it. Now, somebody, help me out. What did we just say earlier? In order to make this a valid, uniform probability distribution, the area of this little block has to be equal to 1. So what's the height got to be? How wide is it? What year is it? How wide is it? 20. 20 times what is 1? You're all like, what is he doing? He's winding something up with this shit. The reciprocal. I like it. 20 times 1/20th is what? 20 times 1/20th is 1. Because the 20s would cancel. Are you guys with me? In fact, that's one way to define a reciprocal. It's the thing that you multiply something by and get 1 as an answer. All right, let me stop there. Does everybody see that? Do you guys see how to get this? I mean, you can actually just make it that always. Figure out how wide it is, and then put 1 over that. You're guaranteed to make it work because that's the definition of reciprocal. It makes it multiply to be 1. What's up? Is that? All right, let's do a quick fire. Here, don't say anything out loud. Do a quick fire here. All right, let's say I have. All right, figure out how tall each of those would be. Don't say anything out loud. I love it when I'm like, don't say anything out loud. The answer's 4. No. What I just said.
I still don't get, the y. Why is it 1 and 20? And does that affect the 20 in the middle?
Doesn't affect it. It is this because of that. So if I knew, let's just, here, watch. If I knew one side of a rectangle was 7, and I knew the area was 14, well, what's this? No, oh my God, I love it. Different entire problem. Is this a probability problem? No. If I knew the area of a rectangle is 14, and this side is 7, how big is this side? 2. Why? Because 2 times 7 is 14. If I knew the area of this was 7, what would this side be?
1.
Do you understand why? 7 times what is 7? 1. I like it. If I knew the area was 1, 7 times what is 1? 7 times 1 over 7. Bam, bam. There, that's all we're doing. That's it. You're going to know the width because they have to tell you between what time and what time, or between whatever this represents. They're going to have to give you that. And most of the time, you have to figure out the height. That step of figuring out the height is called normalizing this. It's that factor I multiply by to make the thing actually become a valid distribution. Force it to be 1. Okay, maybe. Are you guys okay with this? This is not, I don't know if you're making too much out of this. It's not high-level shit at all. So, you're like, shut up, man. You don't know what high-level shit is. What about this? How tall would this be? Who?
1 over 4.
1 over 4. 1 over 4. How wide is it? 4. So how tall does it have to be? 1/4. I mean, that's, you guys see? How wide is this? 13. So how tall is it? 1 over 13. Let me try one more. Okay. What if I had 7.1 to 7.3? I like it. Why am I doing that? Because you're going to see it in the homework. That kind of thing. Same idea. Same idea. How wide is it? 0.2. Now here you do have to do a little bit, please. So you can start with the height being what? 1 over 0.2. You ready for this? What's 0.2 as a fraction? 2 over 10. 0.2 is 2/10. 1 divided by 2/10 is 10 halves. 10 divided by 2 is 5. So it's 5. The smaller the width gets, the taller the height must be in order to make the whole area still 1. Does that make sense? This width is pretty damn small, so the height's going to be pretty damn big relative to what it normally is to make up for that. And what did I do? Did I just do something different? No. It's freaking 0.2, so it's 1 over 0.2, but you better not stop at 1 over 0.2. Shit. Just plug it in the calculator. You don't have to do the stuff I just did, but I hope to God you could. 0.2 is 2/10. You should know that. 1 divided by something is just the reciprocal of that thing. 10 over 2. 5. What's 5 times 0.2? 1. I like it. All right. Yes, ma'am.
So why don't you, like 1 over 4, why don't you just get the answer for that?
1/4 is fine. I mean, there's really nothing to do there. You could make it what? 1/4 is what is a decimal? 0.25. The main problem with this one is this a fraction? I love this. No, it's not a fraction. Why? There's a decimal in it. Fractions are defined to be those things that have whole number ratios, right? So that is the major problem here. Yes? And do you guys, if you don't like what I did earlier, do you know what you could do? Can't you move this decimal over, which means you move this decimal over? 10 divided by 2 is 5.
So because it has a decimal, you have to.
Yes, I love it. In general, you can leave it as a fraction because then you can get kind of exact answers. This one simplifies to a nice whole number. Why the hell not do that? Technically, you get the right answer if you don't, but it's still not good to leave a decimal inside of a fraction. It's not good. Yes? Are you good? Stretching? Okay. All right, so let's come back to my original before we did the lightning round. Okay, now everybody see this is 20, so that's got to be 1/20th. Is that cool? All right. So what is the probability that somebody waits between from 11 to 18 minutes? Now, can you, if you got this picture drawn on your paper, can you indicate that area on the picture? Where is this area on the picture? Where's 11? What's right here? 10. So 11's like maybe right there. Where's 18? Ain't got to be perfect. All right. As long as you don't put 18 here. That always makes me worried about you. 11, 18. So the area we're talking about is right there. Now, did this question suddenly change the probability the shuttle will show up at some time? No. So don't erase this shit and make a new height. No, I don't ask it because that would be neat. Hey, does the shuttle show up in 5? And then suddenly the probabilities all change and it suddenly shows up. I'm like, oh wow, what power? No. It's not some freaky hero thing. Heroes, they were good ones. How wide is this? How tall is it? Still 1 over 20. Of course it is. It's inside that thing. So what's the area of that little block? What's the area of it? It's the width times the height, right? So it's going to be 7 times 1/20. Which is 7/20. I like it. Which is You can just make it into a decimal now, make it look more like a probability. Yeah. Or 35%. I like it. Okay, I like it. How are we doing so far? So again, the basic idea of if I force the area of the picture to be 1, any probability question is immediately related to the area of that section it's asking about. If it's continuous distribution. Okay. Let's try one more of these. Oh, shit. Everybody got what they want here? No? Who said no? Okay. Let me put something over here. You got this? Yes. All right. You guys do this. Let's say. Just make sure you guys are doing this correctly. What's the very first thing you have to figure out? The height. Without the height, you can't answer anything. So don't say it out loud, but that's what you got to figure out first. All right, guys. One thing you'll see here is you can certainly get away without drawing this picture necessarily, but pretty soon we're going to get to a section where the people that make the most mistakes are the ones that skip drawing the picture. The picture is just an anchor of where you are and what the answer should be. So 6 to 7, should that be a very big answer? No, because it's just little slivers from 6 to 7. Oh, no baby sliver. How tall is this sucker, by the way? 1/14. I like it. So then the probability is from 6 to 7 would be. Give you a little help. Yeah, the width is 1 times the height is 1/14, so it's just 1/14, which is what? 0.714? Sounds about right. Or 7.14%. So I take either one of those. Yeah. To be honest, I would take 1/14 also. It's valid. Okay, cool. Yes? What about this guy? Greater than 10. So what's another way to say that makes sense given our picture from 10 to 19? So don't freak out that goes forever. No, not really, because what's the probability? Tell me this, what's probably it's between 19 and 20? I mean, that's zero. There's nothing there. Once you hit that edge, it's zero. There's no probability at all. So greater than 10 is from 10 to 19, basically. And what's the area of that? What's the width? 9. The height? 9/14, which is 0.64. 642. And that makes sense. It's a decent chunk of the picture, right? Okay, I like it. So the picture helps you set up the problem, and then it helps you make sense, make sure the answer makes sense. How are we doing? Is that decent? Here's what you look like when you don't understand. And here's what you look like when you do understand. So, I don't know. I need to figure out how to read mine. Somebody else. All right. Oh, let me ask you this question about this one here. What's the probability that x is less than 4? Kind of gave this away earlier. 0. Now, here comes a freaky answer. Here comes a freaky one. What's probably that x equals 8? I knew it. Yeah, that one stops people cold. Think about this. What's probably x equals 8 to 9? That would be 1/14. Is that cool? It's probably x equals 8 to 8.5. That would be 1/2 times 1/14. 128. It's getting smaller. 8 to 8.1. 8 to 8.01. Holy shit, it's getting smaller and smaller. What's the area at 8? Exactly. How wide is that? 0. How wide is that? It's 0. So probably x equals 8 is technically 0. Why? Now think about it. Why does that make sense? How many numbers are between 5 and 19? And don't give me a finite number. How many numbers are between 5 and 19? Infinite number of numbers. I didn't say whole numbers. I said numbers. So like the number 7.2222222222345 is in there, right? Holy shit. So there's the infinite number of numbers. There's the infinite number of numbers between 0 and 1. Anyway. So what's probably any single one of those numbers happens has got to be basically right next to 0. Because what would be the denominator? Infinity. You guys understand? I'm dividing by the biggest number, so what am I going to get? The smallest number. Now let me just freak out a little bit. There's an idea that's called Iota. That's like the smallest possible number right above 0. It's sort of like the reverse of infinity. We're not going to go there. If you see this kind of question, the answer is 0. For most humans, it's 0. Okay. Please let that make sense. The area is 0, so the answer is 0. Bam. Okay, I like it. So let me let you do this. I'll tell you what. I'm going to do this thing a little bit out of order because I have a feeling we need more practice on this. I thought we might. Number 3 on this page here. Go ahead and try that out. So the side that says binomial and uniform probability practice, uniform distribution. Do number 3 real quick. That's the uniform problem on there.
Number 3, right?
Number 3, yeah. Yep.